In the beginning, I thought that it will be nice to talk about the electrical circuits and what is the simplest electric circuit made up of? Who can tell us? Anna?
Battery.
Can you talk louder, please?
Battery, a resistor, and a switch.
Very good. Okay, so I mean, if this one here is I battery, which is the current coming from the battery and going through my circuit, through my resistor, I call this the conventional current. What is this curly arrow here showing me? A flow of what? What is flowing in the circuit? What is flowing in the circuit?
Electricity? Current electricity?
Right, but I mean the flow of charge, how do we call it with only one word? Electrical what? The flow of charge. The charges which are flowing through the circuit are called
Current?
electrons. Okay, so I was thinking that we would like to make an analogy between water flowing from a heating lower down, and what do I need to put in a circuit, in a mechanical circuit, in order for the water to be able to circulate from the lower level to the higher level and continuously. Can you think about this? I mean, I would like to know, instead of resistor, what would be in the water flow analogy? Instead of the battery, what will I have there? Instead of, let's see, for these most important parts of the circuit. Can you think of anything?
Electron.
Say louder.
Electron.
Right, the electrons are the particles, the charges which are flowing in this circuit, right? And the conventional current has the opposite direction of the electron flow, right? This one here is the electron flow. Right, but if you think of a water flow analogy, what should I think of? Let's see. We talked about this, right? The battery, you see the battery, you see the switch and the light bulb. And then to the right of the slide, what do we have there? The symbols for these elements of circuit, right? Very good. Oh, what do we have here? What do we have here? What do I have in terms of the voltage difference, the potential in my water flow analogy? It was a difference of height between low and high, right? What do I have instead of the battery, instead of the pump? What do I have in my water flow analogy?
You have a pump.
I have a what? A pump, the wheel, right? And the pedal, I mean, okay? So, instead of, what are these positive charges which you see there? What do they represent? But they are positive. Are they representing the electron flow, or are they representing the conventional current? Because if you go back here, you will see that the conventional current is in one direction and the electron flow is in a different direction, right? So what you see here is what? This is the conventional current. Very good. Okay, so let's see. I want to ask you, how can we connect resistors in a circuit? How can I connect them? In series and parallel. Show me very quickly on your whiteboards, how should I do them in series? How should I connect them in series? Okay, very good. Show me your slate. Okay, label them Okay? So this is what I have here. And then very quickly, please show me there how you connect your two resistors in parallel, okay? Do you have the diagram? Yes, do you have them? Okay, let's see. Okay, so the question is the equivalent resistance. I mean, the equivalent, if I have these R1 and R2 in series, you know, here to the battery, what would be the resistance of only one resistor, which I call R equivalent series, to behave in the circuit exactly the same as these two? Which means for the same V battery, I need to have the same current coming from the battery and going through the two resistors. Right? So how can I calculate what is R equivalent? How can I calculate? Are there any laws I need to use? What laws?
Ohm's law.
What is that?
V equals IR.
V equals IR, where V is what?
The voltage of the battery.
Measured in? Measured in? Look on the screen.
Volts.
Very good. And current? Measured in? Amps. Very good. Okay. And resistance?
In ohms.
In ohms. Very good. Okay. So this is Ohm's law. Do I know any other laws? I mean, I don't think this is enough on a parallel circuit. I think I need some other rules. What rules? Do you recall about the junction rule? What does it say? You don't know? It is very similar with the money getting out or coming into your pockets. All of the money which are coming in are good, are plus, positive. All of the money leaving your pockets, this is not good, this is negative, right? So what does this junction rule say? It says that in a junction, which means where more than 3 wires connect, what happens with the currents?
Inner equals outer.
Oh, you know, you know them, but I mean, why don't you express yourself quicker and more precise, right? So you say that, let's see, which ones are here in, which ones are out?
I3 and I1 are
I1 and I3 and I2 is out. Okay, go ahead and tell us what is junction rule. What does it tell us? That I1, this is in, this is out, right? So I1, what's the sign of I1? If it's in, money going in.
positive.
Very good. I2.
Negative.
I3. Very good, equals 0, right? Or in other words, what you told me, I1 plus I3, which are coming in, is the same with what is going out. Is this right? Very good. What about loop rule? What does it say? Here you have our two resistors in series, and it explains you what happens. It explains you how the battery pumps the charges up to a higher potential, and the current then flows through the resistors, and you have a drop of voltage in the resistors. It's losing energy because the resistors dissipates energy, right? Dissipate energy. And this starting level could be regarded as the ground level. Anytime you connect a circuit to ground at some point, you are forcing the potential at that point to be the zero reference level, similar to the zero reference level of gravitational potential, right? So we said that the voltage difference is the same, is similar with the difference in height in the mechanical analogy, right? Okay, so you will have this posted on Moodle, and you can look more. How do you think the pedals will be in a parallel circuit? I mean, can you think? How? One in a row with the other one, or how else?
They'd be equal.
Like this? Will they be located like this? I mean, what I want to ask you, in fact, is you see this diagram here, right? And then for parallel, you see this diagram, right, with your resistors in parallel. I want to ask you, and please talk to your partner and answer my question. What is shared for the series circuit? What is that which R1 and R2 share, have the same? And you will say, what are you asking us about? I'm asking about, what can you say about current? What can you say about voltage drop? Okay, so let's see, look here and tell me. Is the current the same or different through R1 and R2? What can you tell me about delta V? Delta V1, I mean V1 through this one here, and V2 through this one here. Let us, to be simpler, say that R1 equals R2. Right? So you see, you have this one here. This is the diagram. You have R1 and R2 in series, as you told me, right? Okay, what is that which these two resistors share, have the same? Is it the current, or is it the voltage difference? Look there, talk to your partner, go ahead. Raise your hand and give me an answer. Why do they have the same? Here. What is that which they share?
The current.
Say it.
The current.
Are you asking or are you stating?
I'm stating.
Stating. Say it.
The current.
The current is how? For make a sentence.
The current is constant when the resistors are in series.
Right. The current is the same through both R1 and R2 when they are in series. Very good. What about the voltage difference? Let's say that they are the same. I mean, you see, from the battery you have delta V battery, right? And if these ones are the same, of the same value, how much will be at the end of those, across each of them? How much? What will be the voltage drop across each resistor? Can you figure it out just looking at it? How much? Will it be equal or not? Voltage drop across R1 and voltage drop across R2. If the resistors are the same, and if the current is the same, what do you think about the voltage drop? Say it louder, please.
They'd be the same.
The voltage drop will be the same. How much compared to the voltage from the battery?
Would be half.
Very good. Very good. It will be half of what you received from the battery. What rule did you have in mind? Not junction rule, but another rule.
Loop rule.
Loop rule, what does it say? Loop rule, it's easy. It's very easy. Loop rule will say that, look, the sum of all of voltage differences across a closed loop is how much? 0. Yes? Very good. Okay, so once again here you said that the same is the current. And what is here the same for my parallel connection? This one is I battery, and this one here is V battery. What is this which these two resistors are sharing here? Look, I mean, you see this wire comes here, and this wire comes here, and they come from V battery, right? So how much do I have across R1? How much voltage difference? What is the voltage difference across R1?
V battery.
V battery, very good. What is the voltage difference across R2?
V battery.
V battery, very good. Okay, so in this example, what is common for both of them?
The voltage difference.
The voltage difference, very good. Voltage difference, very good. This was a little bit of reminding you about Ohm's law. Let's see if we have it here. Ohm's law analogy. You have what is Ohm's law, what are the equations, what do I mean by voltage, some analogy, mechanical analogy for you to think of it and associate it with not so abstract of an example. You have it here. What is current, what is resistance, and what are their values? And Ohm's law, what did you say Ohm's law is? Oh, I'm sorry, I'm talking without you being part of it, right? So, Ohm's law analogy, right? What is current, what is resistance? Ohm's law, what does this thing show me here? I mean, if I'm talking about current, I want to find out current, you will cover that sector there, and I will be given by what formula? V over R, right? If you want to look for voltage, you will cover that, and V equals
I times R.
I times R. Very good. Okay. Here is what you told me, that it's measured in volts, right? And with the mechanical analogy is the size of the water tank, and current is measured in amps, resistance in ohms, and here is the formula written in 3 different ways, right? Depending upon what you are looking for. Very good. Here you have a more elaborate Ohm's law wheel, which is able to provide you with formula for power, current, resistance, and instead of a V for voltage, you can have the letter E, which is also used for voltage. Here, do you see in the left column resistors in series, and how can we calculate the equivalent resistance of a series circuit? You will apply what laws, what rules? What rules? We just reviewed them. What? Say it.
The junction and the loop.
The junction and the loop, depending upon the circuit. Here it is. This is the loop rule. How many loops do you see to the left of the slide? How many loops do you see up? Only one. And to the right, in the first diagram, how many loops? 2. Okay. Loop rule for the first, explained it here, and using Ohm's law, you have the equivalent for series. Loop rule applied here for the resistors in parallel. Junction rule, very good. This is a review for you in what you already know. Let's see here. This is a combined circuit. I want to ask you, are elements 3 and 4 in series or not? Say it.
Yes.
Yes. Are elements 1 and 2 in series? How is 2? 2 is, what can you say about 2? 2 is connected how? With? Very good. I mean, we don't really have time right now, but you can do this on your own while you are looking for in Moodle, okay? Everything which we talked about is related with direct current electric power, and the next speaker will talk more about AC power. There is not a lot of time here left for me, but I just want to introduce this problem to you. Let's say that we are dealing with a DC problem, direct current, using battery, right? And I want to give you 5 minutes, maybe you can figure this out. We have a box with lots of resistors. And write down please there, the power, here I have a typo, the power each resistor can get is 0.1 watts, 0.1, not 1, okay? And in that box I have 10 ohms resistors, right? So each resistor, I have numerous, I have 1000 resistors there. I want to ask you, how should you connect these resistors to a 10 volts battery, which gives a current of 1 amp in the circuit? Who can figure this out in the next few minutes? I mean, you will say, okay, let's make a plan. Do we have any specific condition? So, what is the maximum power these 10 ohms resistors can dissipate? What is the maximum power? What did I say? It is in the text of the problem. I said it's a typo here. How much did I say? 0.1 watts, okay? Very good. So let's see, what is the plan? First, calculate the equivalent resistance in a circuit which will give you what current from the battery? Look in the data of the problem. How much? 1 amp. Very good. What do you have from the battery? Very good. What is the equivalent resistance? Tell me very quickly. Calculate it. Use Ohm's law. Yes? Use Ohm's law. What is the equivalent resistor? Do you have a circuit? Do you have a circuit? This is what I have, you see? This is my problem, my data. I have lots of numerous resistors of 10 ohms. I know that from the battery I have 10 volts. I know that the current from the battery is 1 amp, and I know that each resistor cannot take more than 0.1 watts, right? How should I connect my end resistors? And how many resistors should I use? What is R equivalent? Did you calculate it? Did you calculate it? How much is it? The total R equivalent. 10 ohms. Very good. Okay, but now what you need to do next, you need to figure out how should you connect this in such a way to have how should you connect these 10 ohms? Because you have 10 ohms for each resistor, but I battery is 1 amp. So what would be the current through each resistor? You know, you have this there on Moodle posted, right? And you can think of it. Let's see here. This is the problem, and here is how you solve the problem, right? So let us be nice now and let our speaker invite him.
I'm going to do a little more practical rather than theoretical presentation. It's on generation and the electric grid, where it is today and where it's going. And as many of you know, I'm sure our regular electricity is alternating current, or AC. And we'll just go in a little bit to what the advantages and disadvantages of that are. By far, most of the electric generation in the United States and the world is done with steam turbines. And most of the electricity is now produced with coal. And the coal produces steam at very high temperatures, around 1,000 degrees Fahrenheit, and that's used to drive steam turbines. Steam turbines actually do not have a tremendous efficiency. It's very good for mechanical engines, but it's actually on the average in the order of about 33%, with about 38% maximum. But various kinds of fuels can be used to generate steam, and those include these that you see up here. One of the advantages is that we can actually use the sun with this kind of power, and it produces an electrical output that looks very much like a coal plant, but the only fuel going in is sunlight. And we'll have another session on that. It's called concentrating solar thermal. Another advantage of steam turbines is that they're able to use multiple fuels. All you have to be able to do is to heat the water. So if the sun wasn't shining, we could store that heat in something and use that to generate steam. When the sun isn't shining, if we were using concentrating solar thermal, or we could use natural gas, or we could use some kind of some biogas of some sort, or we could use hydrogen that was produced from renewable electricity at some point in the past. All those could be used for steam generation. Can we turn this light down a bit? Is that possible? Okay. This is a diagram of a modern steam turbine. There are actually a number of sections because the steam starts at a very high pressure and then goes to lower and lower pressures. And the arrangement of the turbine blades and the amount of space the steam goes through for each different pressure there's a different arrangement of turbine blades to get the maximum efficiency. So we want the steam to go from very high pressure to as low a pressure as possible and release all its energy into the mechanical rotation of the turbine. That's the object. So you want to start with a very high temperature and then go to a much lower temperature. And then eventually, the steam that goes through these turbines is not steam as what we often think of as steam, which is actually condensing vapor in the air where you actually see something. If there were to be droplets in these steam turbines with the pressures involved and the speeds of the turbines, it actually would erode the blades. So the water vapor going through these is actually totally a gas. It's sometimes called supercritical or even supercritical steam, however hot it is. At the end, you see the generator. This is essentially a rotary electromagnetic device. It turns the rotary motion into electricity through basically magnetic fields crossing wires within the generator. There has to be motion with reference to the wires, and so the rotary motion accomplishes that in this case. This gives you an idea of the size of the blades in these turbines. They're quite large, quite impressive. This is a full blade assembly being put into a turbine. This is from Siemens, which is one of the manufacturers of these turbines. You see the size again there, and when it's all closed up, it doesn't look nearly as interesting, but this is how it actually would look in the power plant. Now, AC versus DC. How many are familiar with alternating current versus direct current, what the difference is between the two? Well, direct current basically flows in one direction. It would go from, for example, negative to positive terminal of a battery. Alternating current actually alternates direction. That's why it's called AC, alternating current. So in the United States, for example, that happens on our electrical system 60 times per second. It alternates. In Europe and much of the rest of the world, it's 50 times per second. Now, a DC generator would generally have variations coming out. This could be called pulsating direct current, where it's not smooth. And that can be smoothed out partially by the way the generator is made. You can have more windings in there, and partially by using capacitors and inductors to smooth it out. Everyone is probably familiar with what's called an alternator in their car. Alternator is just an alternating current generator. In the car, that's actually turned into DC with what's called a rectifier to charge the battery and so on. But an alternating current generator actually produces electricity that actually shifts direction. Normally this is done with the rotating generators. It comes out as a sine wave, a pretty pure sine wave. A pure sine wave doesn't have any harmonics. If it's 60 hertz, 60 changes per second sine wave, then it wouldn't have much energy at, say, 120 hertz or 240 hertz or odd harmonics. It would be fairly much look like this if you looked at it on an oscilloscope. Now, a long time ago, at the genesis of our electric grid, when electricity was just getting going in consumer use, Thomas Edison put in a system in New York City and other places, systems in New York City and other places that use direct current to be distributed to the households and businesses and so on. Edison was a great experimenter, but he didn't really have a lot of education in science and math like you're getting here. And there were certain things that he didn't realize about alternating current that Nikola Tesla did. Nikola Tesla worked for Edison for a while, and the story is that at one point, Edison told him that if he could improve his generating equipment, that he'd give him a bonus of $10,000. Well, Tesla went away and worked very hard for a year, actually improved the equipment, came back, and Edison said something to the effect of, oh, you don't know what an American joke is, and I'll give you a 15% raise or something like that. And this naturally upset Tesla quite a lot, and he quit, and he worked on his alternating current motors and generators, and he was hired by Westinghouse a short time later and produced the competing system, the alternating current system that eventually won out in not only just the US, but the worldwide electrical grids. This is a 1983 World's Fair electricity exhibit, and you can see on this side is Westinghouse Electric. That's what Tesla was designing for. Behind is General Electric, which is what Edison's company became. So there was this competition between AC and DC on the grid. This is an actual AC generator. I think it was a 500 horsepower generator, circa 1893. This is at the fair. Okay, DC versus AC then. Things have changed a little bit, and we'll go into that soon. Direct current can go a limited distance at the voltage at which you use it. Like in our houses, we're using about 120 volts. 120 volts, a lower voltage will have more loss in the wiring. If you have 100 volts going through an ohm, you have 100 amps. If you have 1,000 volts going through an ohm, you have 100 amps. 1,000 volts going through an ohm, you have 1,000 amps. So you have much less loss if the voltage is higher through your wiring or through any resistance. Now, the distance it was possible to go with these lower voltages without a lot of losses was only a mile or two in practice. And it was also difficult to produce other voltages from that at the time. Alternating current, on the other hand, can be very easily stepped up or down using a transformer that has no moving parts in it. It can be done pretty efficiently. And because the electricity can be stepped up to a much higher voltage, the power stations can serve a much larger area. The losses through the transmission lines would be much less. This is a diagram of a simple single-phase transformer. That's just 2 wires going in with alternating current and 2 wires going out. Now, because the current is always changing, it produces a changing magnetic field, and that cuts across the windings on the other side. The magnetic flux is concentrated by the core, which is usually an iron core in this case. And this flux cuts across the wires on the other side as it increases and decreases, and it produces a voltage on the secondary side. So if you had, say, 1 winding on this side and 10 times as many, or 10 windings on that side, you'd actually have how many windings you had on this side, there'd be some optimum. If you had 10 times as many windings on that side, you get 10 times the voltage coming out. Your current would also be 1/10 as much, so your power would be roughly the same, minus a bit of losses that happen in the wire and the core. Things have changed a bit with DC and AC advantages now. Semiconductor devices have enabled efficient conversion between DC and AC, both ways. This has allowed a number of things to happen. More electrical transmission and distribution options than there used to be. More end-of-use options, greater overall systems efficiency, and this is part of the evolution to the next generation of a smart grid. Most, like your computers, your laptop computers, your iPads, your phones and all, use DC. They use DC in a battery. It would make sense if we could provide DC directly instead of making a transition from AC, where there are usually some losses, to be able to do that. And this is going to be part of what will appear in the FutureGrid, that option. This is a simple diagram of the electricity grid. You have generating stations of various kinds of generators. In this case, you have a step-up transformer. Then you have transmission lines. To go longer distances, it's desirable to have higher voltages. Then you have step-down transformers, which provide voltage for various uses from industrial and commercial to residential. The residential voltages are lower. Sometimes for industrial and commercial use, it's much higher. This is a more comprehensive kind of view of the grid. You have many sources of electricity coming in. You have various voltages and kinds of transmission lines. There are also high voltage direct current transmission lines, which can go longer distances at lower losses, but aren't as good for tying many different sources into. Then you have a transmission grid that's getting it over longer distances. Then you have the distribution grid, that's more local, where it's going to the houses and businesses and area and so on. And the voltage is stepped down to various levels for the distribution. There are actually 3 US electric grids. And they're independent, although they're tied. There's the Eastern, the Western, and the Texas grid. Interestingly, this shows different voltages of transmission lines and proposed new ones. Interestingly, if you see these little black things between the different grids, those are conversions from AC on one side to DC and then back to AC for the next grid. The reason for that is that it avoids the problem of having to synchronize all these 3 grids. Because if they're not synchronized, you have real problems. The AC doesn't properly feed. It will basically cause grid instability. And that's a very great advantage of the ability to convert between AC and DC with these solid-state devices. It was possible to do it with tube-type devices in the past, but it wasn't nearly as efficient, and they weren't able to handle as large powers. This is the electricity flow. This actually, the energy going in and the energy going out into the grid. One thing to note here is that most of the electricity is produced from coal, and then next nuclear and natural gas. But the top is actually energy wasted because of the basically the limitations of efficiency, the second law of thermodynamics. A tremendous amount of energy is wasted. This is the energy going in, and the bottom is the electricity, the energy BTUs of electricity that actually go out. BTUs is a heat unit, but it can be used to measure different kinds of energy. And then you see the different amounts that are used for residential, commercial, industrial, and so on the other side. And some is lost in the grid, but it's actually quite a small amount. The grid is becoming increasingly efficient over time. This is the overall energy consumption of the US by type of fuel. This is not just electricity, it's all different things. Virtually all the coal is used to produce electricity. Some of the natural gas is used for electricity. A lot of that is used for heating. The petroleum is primarily transportation fuel. And most renewable energy is used to produce electricity. This is the sources for electric generation. And one thing to note here, well, you can see that coal and natural gas are the largest, that renewables, aside from hydro, or hydro is not included, renewables are actually very small. One of the kind of artifacts is that the electric companies will tend to buy the cheapest energy, and often renewable energy is more expensive than some other source. So often the full potential of the renewable energy sources that are out there are not used for that reason. You'll see some of that reflected down here. This is the various kinds of renewable energy that are on the grid now, and the percentages. You see wind is by far the largest. And PV is growing very, very fast, but take a while to catch up. Even though the amount of renewable energy is increasing, the actual rate of growth of renewable energy has slowed a bit with the recession and lack of some good policies. Capacity factor is an important thing. If you have a solar panel and it can put out a kilowatt of electricity, 1,000 watts, but it can only run for 5 hours, and that's only 5 kilowatt hours. The capacity factor is how much use you're actually going to get out of that, what's called a nameplate capacity. So some kinds of power can be there much more than others. You see that, for example, hydro can be there most of the time. Geothermal, the earth just remains hot, and so on. To have say a 20 kilowatts of solar panels, you also have to say, well, how much time are they actually putting out 20 kilowatts or some fraction of that? And that would be what the capacity factor is. And if you're going to use so many kilowatt hours, you have to make sure that you have that much. And if you want it out and you don't have another backup source, you have to make sure you can store that much too. This is in the US grid, the peaks. You can see the peaks for summer and winter. The top one is a summer peak. The middle one is a winter peak, and average. This is not actually showing exactly how much electricity. This is showing what percentage of the total generating capacity of the United States is being used at those times. So you can see the summer peak can come pretty close to the full capacity, and that is an issue. And there are many plants wearing out that have to be replaced, and we're making this transition to renewables. And so this is a very real issue now. So there are variations in both the demand, which can be summer, winter, time of day, and so on, and also in the generation resources that are available, particularly in the renewables. What's called usually base load, or plants that run almost all the time. Coal plants are generally considered base load, so are nuclear plants. There are also spinning reserves. These run constantly to adapt to very quick changes. They're kept running, and if some change comes, they can very, very quickly adapt to the need for more electricity, or if some generating plant drops out, they can compensate for that. Peaking plants are usually older, less efficient plants that are just brought online to provide more power when there isn't enough from the baseload plants and the spinning reserves. One thing that you probably know about solar power and wind power is that it can come and go very quickly. That's one reason that these spinning reserve plants are very important right now. In the future, we're hoping that batteries, connecting the batteries of electric cars into the grid using smart grid technologies, will be able to compensate a lot for that, as well as other kinds of battery technologies and storage technologies. On the demand side, there's a possibility, if there's too much load, to say, can you please turn off something? Can you turn off your dryers, your refrigerator, air conditioner? Part of the smart grid technologies is to be able to do this automatically. If a customer agrees that if the load is very high on a very hot day, they'll let you turn off the air conditioner for a half hour every hour or something like that. Then the power company can compensate without putting more power online or straining the grid so much. Okay, I'm going to say this is, right now we're coming from what we could call a dumb grid. You hear a lot of talk about the smart grid. The smart grid is not the only thing about the future grid. There are other things as well. In much of the US and worldwide, the grid is still dumb. Someone has to call a power company, and the power company doesn't know the power has gone down in the area. In a smart grid, the power company would immediately know. All the future enhancements will not be just in smarts. There are other things happening as well. The future grid will continue to add more generation from renewable sources, reduce the amount of fossil fuel use, which will reduce greenhouse gases, and will add transmission capacity for renewable electricity, upgrade the distribution in various ways, and build more resilience. An example would be an islandable microgrid, where you have a unit of the grid that can actually isolate itself and continue to operate without connection to the larger grid with its own power generation and storage. In a smart grid, these are the main elements I came up with. There isn't really such thing as a smart grid per se. It's more applying more intelligence to the electric grid. So these are mainly what you have in a smart grid. You have sensors that gather data of all different kinds, processors that do the intelligence. There are computers, little computers that are embedded in things. There are bigger computers that analyze all kinds of information. A lot of computers. You have controls. If you wanted to shut off that air conditioner out there, you have to have some kind of control to do it. You send a signal and that shuts it off. There has to be communication between everything, and that can go either over the lines themselves or via radio signals or other things. But there has to be some standard way of doing that so everything can talk to everything else. And human interfaces, you have to be able to interact with the system either manually or say that this is what I want you to be able to shut off and not, and during the schedule and things like that. And also the people at the power company and all have to be able to do that as well. These are basically the scope of smart grid concerns, which is a good way to put it. This is what the reason behind developing smart grid technologies. You're automating as much as you can, and you're trying to bring in more renewable energy, make the operation of the whole grid more efficient, more resilient, less likely to have outages. You've probably heard of some of these cascading outages where one thing goes down and something else does. In a smart grid, you'd have much more quick detection of things like that and the ability to very quickly react to those things. And then smart appliances, distributed generation, which is where you'd have it on your house, for example, solar panels on your house, energy efficiency. If the system knows what's going on in your house, it can turn things on and off or regulate the amount of electricity being used, and so on. And also integrating cars into the grid is going to take considerable, and their batteries into the grid will take a certain amount of smarts. These are characteristics of the future grid, really. It's, let me see. Yeah, let me just redo things here. I guess you can see those things pretty well. It's actually just implementing a number of measures, including the smart grid technologies, just to improve both the functioning capacity of the grid and the customer interaction with it. That's just a quick rundown. Any questions on that? I know it's a lot of just general information. Yes?
So for the human interfaces that you were talking about on the grid side, like is that on the distribution scale, like would that be distribution center, or is that for the power generating?
Yeah, actually, that's a good question. You would have human interfaces at both of those points. On the grid side, you have to have them monitoring the grid and regulating its operation. And on the customer side, there are a lot of things you can do. For one thing, it would be very useful to you to know how much power you're using from things and to have a display that tells you, or some readout that tells you, this much electricity is being used and it's this device that's using it, and so on and so forth. Or for example, you could have it automatically regulate your heating and cooling, your lights, and things like that. You could, if you were on a program to, say, allow the power company to shut down your water heater or air conditioning at times of peak demand, you could say, I want that, but I only want it at these times, or you could say, I don't want that right now. So you'd have your own options there.
For the smart grid, like how intelligent would it be? Like would it be able to control this? If you know that one area that doesn't need as much power, so would it be able to redistribute that power, or would that have to be manually done?
Would that have to be what?
Manually done.
Oh, no, that could actually be done automatically. There really isn't much of a limit to how much intelligence can go on the grid. The microprocessors have become extremely inexpensive, as have many solid-state devices, and are built into many things now. New appliances will have basically smart grid technologies built in. So there is a possibility of a tremendous amount of automatic control. The reason for the human interface part is more to tell it what you do and don't want it to do. Like if it has automatic capabilities, then that would allow you to say, these are the parameters I want to set for those automatic things that are going on. But it can be extremely intelligent. There really isn't much of a limit to that. It's a good question. Any other questions? I think I went a bit long. Thanks for staying with me.